say I've got some matrix A. It's an n by k matrix. Let's say it's not just any n by k matrix. This matrix A has a bunch of columns that are all linearly independent. So A1, A2, all the way through AK are linearly independent. They are linearly independent columns. Let me write that down here. So A1, A2, all the column vectors of A, all the way through AK, are linearly independent. Now, what does that mean? That means that the only solution to x1 times a1 plus x2 times a2, that's a 1, plus all the way to xk times ak, that the only solution to this is all of these x's have to be 0. So all xi's must be equal to 0. That's what linear independence implies. Or another way to write it is all the solutions to this equation, x1, x2, all the way down xk, equaling the 0 vector, that all of the solutions to this are all of these entries have to be equal to 0. This is just another way of writing this right there. We've seen it multiple times. That's the 0 vector right there. So if all of these have to be 0, that's like saying that the only solution to ax is equal to 0 is x is equal to the 0 vector. Or another way to say it, and this is all coming out of the fact that this guy's columns are linearly independent. So linear independence of columns, based on that, we can say since the only solution to ax is equal to 0 is x is equal to the 0 vector, we know that the null space of A must be equal to the 0 vector. Or it's a set with just the 0 vector in it. And that is all a bit of review. Now, n by k, we don't know its dimensions. It may or may not be a square matrix, so we don't know necessarily whether it's invertible and all of that. But maybe we can construct an invertible matrix with it. So if we take A, let's study A transpose times A. A transpose times A. A is an n by k matrix. A transpose will be a k by n matrix. So A transpose A is going to be a k by k matrix. So it's a square matrix. So that's a nice place to start for an invertible matrix. So let's see if it is actually invertible. We don't know anything about A. All we know is its columns are linearly independent. Let's see if A transpose A is invertible. Invertible. And essentially, to show that it's invertible, if we could show that all of its columns are linearly independent, then we'll know it's invertible. If we have any, and I'll get back to this at the end of the video, but if you have a square matrix, with linearly independent columns, remember the linearly independent columns all are associated with pivot columns when you put them in reduced row echelon form. So if you have a square matrix, then you're going to have exactly, so if it's a k by k matrix, that means you're going to have k, that means that the reduced row echelon form of matrix will have k pivot columns, and be at k by k, and be a square k by k matrix. And there's only one k by k matrix with k pivot columns, and that's the identity matrix. And that is the identity matrix, the k by k identity matrix. And if when you reduce something to reduced row echelon form and you get the identity matrix, that means that your matrix is invertible. That means it's invertible. I could have probably left that to the end of the video, but I just want to show you, if we can show that we already know that this guy is square, that A transpose A is a square matrix. If we can show that given that A has linearly independent columns, that A transpose times A also has linearly independent columns, then given that the columns are linearly independent and it's a square matrix, that tells us that when we put it into reduced row echelon form, we'll get the identity matrix, and that tells us that this thing would be invertible. So let's see if we can prove that all of this guy's columns are linearly independent. So let's say I have some vector v, let's say my vector v, is a member of the null space of A transpose A. That means that if I take A transpose A times my vector v, I am going to get the 0 vector. Fair enough? Now, what happens if I multiply both sides of this equation times the transpose of this guy? So I'll get v transpose. Actually, let me just do it right here. If I multiply v transpose on this side and v transpose on this side. And this is, you could view this as a matrix vector product, right? Or in general, when you take a, if you take a row vector times a column vector, it's essentially their dot product. So this right-hand side of the equation, you dot anything with the 0 vector. This is just going to be, that is just going to be the 0 vector. Now, what is the left-hand side of this going to be? We've seen this before. If you have the transpose of, we could view this as, even though it's a transpose of a vector, you could view it as it is a row vector, but you could also view it as a matrix, right? A column vector is a, let's say V is a k by 1 matrix. V transpose would be a 1 by k matrix. Anyway, we've seen this before, that is equal to the reverse product, the transpose of the reverse product. Or if we take the product of two things and transpose it, that's the same thing as taking the reverse product of the transposes of either of those two matrices. So given that, we can replace this right here with A times the vector v transpose, and we're multiplying this vector. We're multiplying this vector times AV times this vector right here. And that is going to be equal to the 0 vector. Now, what is this? If I'm taking some vectors transpose, and let's say, this is a vector. Remember, this is, even though I have a matrix vector product right here, when I multiply a matrix times this vector, it will result in another vector. So this is a vector, and this is a vector right here. And if I take some vector and I multiply its transpose times that vector, we've seen this before, that is the same thing as y dot y. These two statements are identical. So this thing right here is the same thing as AV dot AV. This is the same thing as AV dot AV. And so what does the right-hand side equal? The right-hand side is going to be equal to 0. Actually, let me just make a correction up here. When I take v transpose times the 0 vector, v transpose is going to have k elements, and then the 0 vector is also going to have k elements. And when I take this product, that's like dotting it. You're taking the dot product of v and 0. So this is the dot product of v with the 0 vector, which is equal to 0, the scalar 0. So this right here is the scalar 0. I want to make sure I clarified that. It wouldn't have made sense otherwise. So the right-hand side, when I multiply the 0 vector times the transpose of v, it gets just the number 0, no vector 0 there. So this AV.AV is going to be equal to 0, or we could say that the magnitude of or the length of AV squared is equal to 0. Or that tells us that AV has to be equal to 0. The only vector whose length is 0 is the 0 vector. So AV, let me switch colors. I'm using that a little bit too much. So we know that AV must be equal to 0, to the 0 vector. Right? This must be equal to the 0 vector since its length is 0. Now, we started off with saying V is a member of the null space. Is a member of the null space of A transpose A. V could be any member of the null space, of A transpose A. But then from that assumption, it turns out that V also has to be a member of the null space of A. That AV is equal to 0. So let's write that down. If V is a member of the null space of A transpose A, then V is a member of the null space of A. Now, our null space of A, because A's columns are linearly independent, it only contains one vector. It only contains the 0 vector. So if this guy is a member of the null space of A transpose A, and he has to be a member of the null space of A, there's only one thing he can be. There's only one entry there. So then V has to be equal to the 0 vector. Or another way to say that is any V that's in the null space of A transpose A has to be the 0 vector. Or the null space of A transpose A is equal to the null space of A, which is equal to just the 0 vector sitting there. Now, what does that do for us? That tells us that the only solution to A transpose A times some vector x equal to 0, this says that the only solution is the 0 vector, is x is equal to the 0 vector, right? Because the null space of A transpose A is the same as the null space of A, and that just has the 0 vector in it. The null space is just the solutions to this. So if the only solutions to the null space is this, that means that the columns of A, of A transpose A are linearly independent. You could essentially write all of the linear combinations of the columns by the weights of the entries of x. We actually did that at the beginning. It's the same argument we used up here. So if all of their columns are linearly independent, and I said it over here, A transpose A has linearly independent columns, and it's a square matrix, that was kind of from the definition of it. So we now know that A transpose A, if I were to put it, let me do it this way. That tells me that the reduced row echelon form of A transpose A is going to be equal to the K by K identity matrix, which tells me that A transpose A is invertible, which is a pretty neat result. I started with a matrix that has linearly independent columns, so it wasn't just any matrix. It wasn't just any run-of-the-mill matrix. It did have linearly independent columns, but it might have weird dimensions. It's not necessarily a square matrix. But I could construct a square matrix, A transpose A, with it, and we now know that it also has linearly independent columns. It's a square matrix, and therefore it is invertible.